Alright, I'm Selma Quintero, and this is my installation project for heat and mass transfer. So first I'm going to give a background on energy and security. So energy security is a multidimensional construct that describes interplay between physical conditions in housing, household energy expenses, and energy-related coping strategies. Quoted by Hernandez. So there's plenty of adverse effects such as like financial strain, uncomfortable living conditions, increased resource usage, and then of course health concerns during harsh weather conditions. These all can be a result of energy insecurity. So this trend has arisen over concerns for the need for easily available and reasonably priced solutions to increase affordability, lower energy usage, and improve energy efficiency, particularly for households facing financial constraints. So of course, we've seen the importance for the households facing financial constraints. If we look over here on this data pulled by Harvard data analyst Frost, that households that range within the income of $25,000 they had to reduce expenses on necessities to pay energy bills. That's roughly 51%, which is just a little bit over half, which is quite concerning. And then even within the $35,000 range, a little bit more, it's still roughly in the 40 to 50% range, roughly in the 40% range. So the societal implications of energy insecurity. So multiple studies have established the links between energy insecurity and the adverse outcomes with mental health, respiratory health, stress, sleep quality, and then of course child health. This is quoted by Hernandez again in a separate article. So when energy insecurity limits a household's ability to maintain comfortable living conditions, it can have a butterfly effect, a string of multiple adverse effects. Like it could potentially lead to social isolation. You may not want to invite family and friends over if you have an uncomfortable house, like it's too hot or too cold. It could also have an impact on productivity, comfortability, especially if you're working from home and that sort of scenario. That could lead to adverse effects in educational and occupational performance. Of course, those effects lead to then financial strain, which of course leads to a plethora of additional issues. And these can all happen from discomfort due to suboptimal living conditions. Inadequate heating and cooling can also consequently put an individual at increased risk of temperature-related illnesses and enhance the effects of these illnesses as well. So we're going to discuss now single versus double pane windows. So this is an impactful change that could be made to promote energy security. This is because single pane windows only have one layer of glass to their construction, which leaves very little insulation. This of course causes problems regulating indoor temperatures. There may be drafts in your house, uneven heating, of course. Double pane windows, on the other hand, provide better insulation and effectiveness in preserving a more consistent interior temperature. That's because it's two layers of glass with a insulating air gap in between. This air gap acts as a layer of insulation by creating a barrier that limits the direct transfer of heat via conduction, heat transfer. This air gap also creates a barrier that limits the movement of air, which can minimize the heat transfer through convection as well. With double pane windows, you can reduce energy consumption up to 24% in cold climates and then 18 in warm. This also leads to savings to 30 to 50% in energy expenses. This is from Pros and Cons of Double Pane windows. So this is our model right here of our problem. you could essentially model this as a double pane window if we were to think of this as a glass pane, that air gap of insulation and then another glass pane, except this is steel plates and fiberglass. So these are this is the conductivity across. Of course, we have conduction in parallel with the steel bar and the fiberglass insulation. And there's a temperature difference on, from each side of 22 degrees Celsius. Okay, so this is a finest and original problem. So we have our steel plates. That's all the parameters that we input into the equation to solve resistivity. And then we have our insulation, steel bars that goes in our resistance tube, combined in parallel there. And then we have our steel plate tube, which is the final one, with the same parameters and resistivity as the first one. So with the metal bars in parallel, we can see that we have a heat transfer of 486 watts. And then in that original problem, they asked us to solve the fiberglass insulation with the steel bars present and without the steel bars present. So as you can see here, when we calculate our heat transfer with the fiberglass without the steel bars present, just the fiberglass within that void space of the cross section, we can see we have a heat transfer of 92 watts, which is pretty significant considering that that fiberglass without the bars only consisted of 1% of the total void space in that cross section. So first, we're going to go with our first parameter change. So this is our material change. So I decided to go with a very extreme material change. I went with one of the most conductive materials versus one of the least conductive materials. So I decided to go with copper insulation. So this copper insulation was calculated in the way of the fiberglass without the bars. We're assuming that this entire void space does not consist of any bars going across the cross section, any steel bars. The whole void space consists of only copper. Same thing with this fiberglass. So I have those same results there. So we have our steel plate, of course, and then our fiberglass without the bar. When we calculate that heat transfer, we end up with 92 watts, as discussed in the previous slide. But as you can see with our copper insulation, we have a heat transfer rate of 166,000 watts, 166,736 watts with the copper insulation, which are obviously two very big extremes. As you can see here, I graphed it on a 3D graph. When I tried to graph it 2D, you couldn't even see the results of the fiberglass, so just 3D at least shows that there is something there. And there's a massive difference between 92 watts at a heat transfer rate of 92 watts versus 166,000. So that's why we can see we use copper, within our wiring and a bunch of other things like heating coils. That's why we use that material versus fiberglass as insulation to stop heat transfer. So that K value is very important. So parameter change 1. This is the first actual parameter change that is in the material. So right here what I did is I increased the insulation and steel bar thickness. So essentially I increased the distance between the two steel plates, steel plate 1 and steel plate 2, and just assumed that it was the same amount of material in between, or that material essentially filled that additional void space. So here are the results there. So as we increase the thickness of our insulation, we see a exponentially decaying trend line with the heat transfer, which means our heat transfer is decreasing at an exponential rate, which is very good if we're talking about trying to dissipate heat rapidly. And then we can see our equivalent as we increase this thickness increases linearly, which means our resistance is increasing linearly in a linear fashion, while the heat transfer is decreasing exponentially in a decaying fashion. Then we have parameter change too. So I essentially just increased our delta T. So I changed the variation of temperature between the two sides. So right here, we increased of increments of 4 of our delta T. And based off our results, we can see that our heat transfer increases linearly as our variation in temperature changes. So this really shows, like, during those extreme winter months, how much more important it is to have that insulation present within your home, because that heat is going to be leaving into that cool environment at a much faster rate. And then basically what I did for this third parameter change is I increased the outer plate thickness. So essentially, here's our model. I just increased the thickness on both outer plates by the same increments. So we can see here, as we increase the thickness of our metal plates, we do decrease heat transfer, but not by a significant amount. We go from only 486 watts to only 465 watts, which is a difference of roughly 20. As opposed to the exponential decaying trend line that went from 486 to roughly the 70, 80 range. So yeah, we see that linearly decaying trend line as the outer plate thickness decreases or increases. We also can see that our delta T for these steel plates also increases too as they take on more heat, but not a significant amount, of course. So here are the experiment results. So parameter change, increasing the plate thickness. So we saw that linear fashion, the linear decay, but not very significant changes. So probably isn't a very good idea to do that if you're trying to dissipate heat or reduce heat transfer, essentially. Parameter change with increasing the temperature differential. So we see that heat transfer rate increased linearly. Parameter change with increasing the width of the insulation area. That's what the bars included, the steel bars included. The equivalent resistance increased linearly, and then that heat transfer rate also began to decay exponentially, as we saw. And then the parameter change, the steel bars removed from fiberglass cross section. So that's when we compared our heat transfer rate of the cross section with the steel bars present, and then without the steel bars with just that insulation engulfing that entire void space. The heat transfer rate, of course, decreased significantly. So this is how our findings can be applied to help with the problem of energy insecurity. So with that heat transfer rate increasing as the temperature differential becomes greater, that kind of shows the importance of having good insulation in these harsh weather months, and also making sure, like double pane windows, for example, that'll save significant money, especially if you're living in more extreme environments. That exponential heat transfer decay, of course, That's the importance of increasing insulation thickness, making sure you have the right thickness of insulation when you are insulating your house, of course. That's the most important factor, and we're trying to decrease our heat transfer rate, as you saw experimentally. The linear heat transfer decay from the outer layer thickness, that shows that that really doesn't have a significant impact, and that really shouldn't be considered a solution if you're trying to decrease that heat transfer rate. And then the copper versus fiberglass, that just shows how important it is to be selecting the right sort of insulation material. So of course that K value, the conductivity, that has a very big factor. And then removing the steel bars from the insulation layer, that shows the importance of using as much insulation material within that void space of that provided layer. So if you do want an insulating layer, make sure it's all insulation and nothing else. You know, that's how you make sure you have the most efficient insulation between two different boundaries. And that concludes my insulation project. These are my sources cited. Yeah, thank you.